Here's an second example of the remainder theorem with synthetic division. This one's a little bit more challenging because the factor does have a radical. So here's our example. Use synthetic division to show that x is a zero of a third degree polynomial. Use that result to completely factorize it. And then this time let's list all the zeros of the function. So we say that our factor is x equals 2. So in factored form, it would be x minus the square root of 2. This is one of the zeros. So this is our constant k. So k equals the square root of 2. Now we take our coefficients, 1, 2, negative 2, and constant of negative 4. Now we do our synthetic division. Bring down the 1. Multiply 1 times square root of 2 is square root of 2. Now we have to be careful when we multiply and add with radicals. 2 plus the square root of 2 is 2 plus the square root of 2. So I'm just going to leave that as a parenthesis. Now we multiply in front. I would recommend that you do this off to the side. So I'm going to take square root of 2 times 2 plus the square root of 2. We're going to distribute in. Square root of 2 times 2 is 2 square roots of 2 plus, I just lost my board connection, square root of 2 times square root of 2 is square root of 4, which is 2. So we have 2 square roots of 2 plus 2. 2 square roots of 2 plus 2. When we add this column here, those two negative 2 and positive 2's cancel out. So we're left with 2 square roots of 2. Now multiply. 2 square roots of 2 times square root of 2. Be careful, you always multiply like parts together. I'm going to throw a 1 in front. 2. And then square root of 2 times square root of 2 is square root of 4, or 2. So 2 times 2 is 4. Add the column, negative 4 plus 4 is 0. The remainder is 0. Now I'm just going to erase this stuff here, just to add some room. That was kind of like my scratch paper. And we've shown that this is a remainder of 0, so it is factorable. This is a 0 of the function. We took out an x minus 2. Here's a piece that we haven't talked about yet. Radical zeros always occur in pairs. So if we said that we had a factor at x square roots of 2 in the green here, then we have to have, kind of like think about it as a conjugate, we'd have a negative square root of 2. This is also a 0. So this is a factor of x plus the square root of 2. So we're going to factor out again using synthetic division. We don't have to start over again. We can work with what we're left with. So we're going to drop a degree. Since our degree before was a cubed, now we're at an x squared, an x, a constant, and then our remainder. So it's 1 x squared, 2 plus 2 square roots of 2, and then c, which is 2 square roots of 2. And we're factoring out by a k, which is negative square root of 2, or as a factor, x plus the square root of 2. I always do the opposite of its factor, but that's the 0. All right, so let's do our synthetic division again and see that this remainder is 0. So we'll bring down the 1. 1 times negative square root of 2 is negative square root of 2. When we add these columns together, those two cancel. Positive square root of 2, negative square root of 2. So we're left with just 2. Then multiply. 2 times negative square root of 2 is negative 2 square roots of 2. When we add that column together, 2 square roots of 2 minus 2 square roots of 2 is 0. The remainder is 0 again. Great. So now we're going to drop the degree. So now it's an x constant remainder. So in factored form, we had x plus square roots of 2, x minus square root of 2, and this remainder right here, 1x plus 2, as zeros. X equals negative square root of 2, positive square root of 2, and this one right here we have to solve for x. So x plus 2 equals 0, so x equals negative 2. So the zeros of the function are negative 2, positive square root of 2, and negative 2.